All right, so this video we're going to go over polynomial functions. All right, and the LEQ for this lesson is how do I classify, graph, and describe end behavior of polynomial functions. All right, here's your vocabulary. Make sure you write these down. A monomial is a single term. This term can be a number, variable, or a product of a real number and a variable, such as something like 2x. Degree of a monomial slash polynomial is simply the highest exponent, which we represent with n. Now, if you have a constant, you still technically have an exponent. For instance, something like, say, 7. This is really 7x to the 0. So the degree here would be 0. So constants always have a degree of 0. Turning points. Turning points are the places where the graph changes direction, and the number of turning points is equal to n minus 1. So the degree minus 1. So if you have a third degree polynomial, which means your highest exponent is a 3, you're going to have a maximum number of 2 turning points. If your degree is 4, you're going to have a maximum of 3 turning points. And then end behavior. It's simply the directions of the graph to the far left or the far right. We'll get into that a little bit later in the video if that's confusing. All right, now this is also a vocab word, but I wanted to give you this picture as well. So it's called the standard form of a polynomial function. That's what's highlighted right there is your vocab. It arranges the terms by degree in descending numerical order. A polynomial function p of x in standard form is, now basically all this says is you just write your exponents in descending order. Doesn't matter what your coefficients are. You just write your exponents in descending order. That is standard form. So like 4x cubed plus 3x squared plus 5x minus 2 is in standard form, where if you switch these two terms, it wouldn't be in standard form. That's all this is telling you. Now, classifying polynomials by its degree or the number of terms. So if you have a polynomial which is a constant, which is just a number, remember I said it has degree 0, there's one term, so it's a monomial. All right, mono meaning 1. Right here we have x plus 4, so we have 2 terms. And this one has a degree of 1 because it's x to the first. Since it's a first degree polynomial, it's a linear polynomial. There's 2 terms, which makes it a binomial. Okay, because bi means 2, like a bicycle has 2 wheels. All right, so here we have 4x cubed. We just went over quadratics, so you know a polynomial that has a degree of 2 is called a quadratic. Like I said, the degree is 2. Now, but here there's only one term, so this is still considered a monomial because there's only one term. Yes, it's a quadratic, so you'll still get the graph of a parabola, but since there's only one term, it's called a monomial. All right. Degree 3 is a cubic. Here's an example of a cubic, 4x cubed minus 2x squared plus x. Since it has 3 terms, this one's called a trinomial. Here again, we have what's called a quartic, because it's a 4th degree. Okay, 2x to the 4th plus 5x squared. But again, it only has 2 terms, so you would call this a binomial. If this had a 3rd term, it would be a trinomial, and it would still be called a quartic. Now, a quintic is your exponent. Since this is negative x to the 5th, your degree is 5, so it's a quintic. Again, if you count the number of terms, there's only 4 terms, so this is just called a polynomial of 4 terms. After you get above 3, it's just a polynomial of however many terms you have. These won't change. You have constant, linear, quadratic, cubic, quartic, quintic of degree 0, 1, 2, 3, 4, 5. Those won't change. But according to your number of terms, you either have a monomial, a binomial, a trinomial, or a polynomial of x number of terms, however many terms you have that is 4 or above. Okay? All right, so here we go. Classifying polynomials. So we're going to classify these by their degree. So we can make this a little easier by rewriting these in standard form. So this first one here, letter A, would go to 9x squared plus 3x plus 5 to get it in standard form. Now all you simply do is look at your largest exponent. So this has a degree of 2. There's 1, 2, 3 terms. So this is a trinomial. Now, since it's second degree, that means this is also going to have 1 turning point. I guess I should write the word point. All right, it's going to have 1 turning point. So it's a second degree because your highest exponent's 2. There's 3 terms, so it's a trinomial. And then your number of turning points, remember, is basically your degree minus 1. So there's 1 turning point. Now for this one, if we write it in standard form, we have x to the 4th. Now, negative 6x squared and plus 10x squared gives you plus 4x squared plus 4x minus 12. So here we have a degree of 4 because that's our highest exponent. We have 1, 2, 3, we have 4 terms, so we have a polynomial of 4 terms. Or you could just call this one a polynomial. I'm not going to get this picky with you. And then since it's a 4th degree, 4 minus 1 is 3, so we have 3. I'm going to label them TP. We have 3 turning points. All right. So that's really all there is to classifying polynomials. It's really all there is to classifying polynomials. So do these 2 real quick. All right, for letter A, we're going to have 5x to the 4th plus 3x cubed minus x. So the degree is 4.
If anybody would like to change their...
All right, so like I said, this one's degree 4. We have 1, 2, 3 terms. So this is a trinomial. And since it's a 4th degree, we have 3 turning points because 4 minus 1 is 3. This one here has a degree of 5 because 5 is our highest degree. This one has 1, 2, 3 terms, so this one is also a trinomial. You might be, Mr. Allison, there's 4 there. Yeah, but if you can add the 3 to the 10 and make this negative 4x to the 5th plus 2x squared plus 13. So therefore we have 1, 2, 3 terms, so it is a trinomial. And since the degree is 5, we're going to have 4 turning points. All right. So like I said, classifying polynomials, not that difficult. Make sure in cases like this, though, you simplify them down. Like in this case, adding the 3 to the 10, just simplify them down. So that way, now we only have 3 terms, which makes it a trinomial. All right. All right. This slide talks about turning points, okay, and it also helps lead into my topic of end behavior. All right, when you have an even degree, see here how the degree here is 4. When you have an even degree, and I got a chart that says this on the next page. Let me copy it over to this page. Move this over, paste. All right. Come on. There we go, close enough. All right, so when you have an even degree, all right, and your leading coefficient is positive. So here we have a positive leading coefficient and an even degree. So our end behavior is going to be called up, up, meaning the left side of the graph points up, the right side of the graph also points up. All right, so when you think even, think equal. They go the same direction. All right, even, equal, they go the same direction. So they both go up. Now, if you have a negative leading coefficient, such as in this case, we have negative x squared, the only difference is instead of going up, up, they're going to go down, down. So they're still going to go the same direction, they're both going to go down. When you have an odd degree, like in this case, we have y equals x cubed, so we have an odd degree. When you have an odd degree and a positive leading coefficient, the left side's going to go down and the right side is going to go up. So here's a nice example of that. Y equals x cubed, it goes down on the left, up on the right. And then here we have a negative, so all that does is flip it over. Instead of going down, up, it will go up, down. All right. And if you look here, your turning points, we have a third degree, we have 2 turning points. We have a second degree, we have 1 turning point. A fourth degree, we have 3 turning points. But then if you look here, we have a third degree with no turning points. That's because your turning points not only equals n minus 1, but also every number less than that, less an even number. What do I mean by that? So for a third degree polynomial, you're going to have n minus 1 turning points. So you're going to have a maximum of 2 turning points. Now, with that being said, if you subtract 2 from this, so minus 2, you could also have 0 turning points. This is a good example. Both of these are a good example of that. Here we have a third degree with 2 turning points. Here we have a third degree with no turning points because the graph doesn't change direction. When I mean change direction, I mean change from increasing to decreasing or vice versa. All right. So here we have a fourth degree polynomial. So with a fourth degree polynomial, you're going to have 3 turning points, or each number below that less an even number. So if we subtracted 2 from this, we could also have 1 turning point. Now, you're never going to have less than 0, and you're never going to have more than your degree. So it's going to be the number right below your degree. So in this case, it's going to be, if your fourth degree, it's going to have 3 turning points, and it will always have, and in an even degree, you'll always have greater than 0. You'll always have at least 1. But for an odd degree, you can have, like for this case, a cubic, you can have 2 turning points or 0 turning points. All right. So if it was a fifth degree, you'd have 4, 2, or 0. If it was a sixth degree, you'd have 5, 3, or 1. You following me there? Good. All right, let's keep rolling here. So describing in behavior of polynomial functions. Now, we are not going to check these on a graphing calculator. I just noticed that was there. So in behavior of a polynomial function with leading term ax to the n. So here we go. Here we have an odd degree. So we need to determine the end behavior. Well, since we have a positive leading coefficient, all right, we have a positive leading coefficient, LC, positive leading coefficient, and we have an odd degree. If we go up here, positive, odd degree, it's going to be down, up. And yes, you can use arrows. All right. So positive leading coefficient, odd degree, and behavior is going to be down, up. Here we have a negative leading coefficient, and we have an even degree. So negative even, it's going to be down, down. All right. Negative leading coefficient, even degree is going to be down, down. Letter A, positive leading coefficient, odd degree, it's going to be down, up. All right. Down, up. So make sure, I would copy this chart down in my notes. Make sure you have that because you're going to be referring to it. I would suggest memorizing it. It's not that hard, so I would suggest memorizing it. But for now, at least write it down in your notes until you get it memorized. All right, go ahead and do this one. Consider the leading term of y equals negative 4x cubed plus 2x squared plus 7. What is the end behavior of the graph? Go. All right, so we have a negative leading coefficient. We have an odd degree. So if you look at your chart, negative leading coefficient, odd degree. It should be up and down. Up, down. Now, if you are going to use arrows, or if you're just going to use the words up, down, always, always, always put the left on the left-hand side and the right on the right-hand side. All right, that's the standard way to write this. When you're talking about end behavior, you write the left end behavior first, and you write the right end behavior second. Okay? All right, so for this one, like I said, negative leading coefficient, odd degree, it should be up, down. All right, up, down. All right, graphing cubic functions. So what is the graph of each cubic function? Describe the graph including end behavior, turning points, and increasing and decreasing intervals. All right, so the easiest way to graph these without a graphing calculator is to just make your good old-fashioned table of values. All right, I know you know how to make a table of values, so I'm not going to go over that, but you just make your good old-fashioned table of values. After you get your table of values, you just simply plot your points, connect with a smooth curve. Now, with this one, our end behavior, of course, we know is down, up, and we know there's no turning points. Now, as far as the increasing or decreasing intervals, this is what I'm going to tell you to do to determine whether it's increasing or decreasing. Imagine you're a hiker, or you know somebody who likes to hike, and you're walking along this graph. If you're walking upward, it is increasing. If you're walking downward, it's decreasing. And make sure you always go left to right. Make sure you always go left to right. If you're walking upwards, it's increasing. If you're walking downwards, it's decreasing. So to describe this, the end behavior is down, up. There are no turning points because you would continually walk up on this entire graph. You would never walk down. So therefore, the function is increasing from negative infinity to positive infinity. Now, this negative infinity to positive infinity, is based on your x values. All right, negative infinity is all the way this way. This graph is going to keep going this way, and it's going to keep decreasing. Okay, and if you go far enough, you can get to very high values. Same thing this way. It's going to keep increasing this way. If you keep going positive, it's going to keep increasing. Okay, so this function, if you were to start walking way over here, you're going to increase over the entire value, or over the entire range of this function, which is negative infinity to positive infinity. Okay? All right, so for the second one here, again, here's your table of values. Here's your graph. All right, so you can see we have two turning points, and they are clearly at -1, -2, and 1, 2. So therefore, we have two turning points. Okay, our end behavior is up, down, of course, your two turning points. Now the function, if you're walking here, you would decrease from negative infinity to -1. You would increase from -1 to 1, and then you would then decrease from 1 to positive infinity. All right. So like I said, for increasing, decreasing, just imagine you're walking on the curve. Just imagine you're walking on the curve, and that will let you know if you are increasing, decreasing, or what's called constant. If you're not moving up or down, you're constant. You really won't see that though with polynomial functions, the constant part. All right. All right, moving right along. All right, using differences to determine degree. All right, this is a lot easier than it sounds. So if we look at this polynomial function that generates the data to the right, we need to figure out the degree. So if we look over here, if we look at this chart over here to the right, all right, we have -3, -1, -2, -7, -1, -3, 0, 5, 1, 11, 2, 9, and 3, -7. Now, we want to determine the degree of this polynomial. We're not going to figure out the function. We're not going to figure out the graph, although we could because we have the values. All we are going to do is figure out what is the degree of this function. Well, it's easy. What you want to start with is writing down all your y values. All right, you want to write down all your y values in a column like we did here. All right. Now, the next thing you want to do is you want to find the difference between each number. So the difference between -1 and -7 is -6. The difference between -3 and -7 and -3 is 4. The difference between -3 and 5 is 8. 5, 11 is 6. 11 and 9 is -2. And 9 and 7 is -16. You see how all those numbers are different? That means we have to take the second difference now. So take the difference between all of these numbers. All right, so difference between -6 and 4 is 10. 4 and 8 is 4. 8 and 6 is -2. 6 and -2 is -8. -2 and -16 is -14. Okay, so there, if you notice, our differences are still different. All right, the first difference, they're all different. The second difference, they're all different. So we need to go to the third difference. So the difference between these two is -6. Between these two is -6. Between these two is -6. Between these two is also -6. So now the difference between each number is the same. Okay? The difference between each number is the same. So what you want to do when you have a table of values to figure out the degree of the polynomial is you simply start taking the difference between successive y values. So we started that here. All right, the difference between these two is -6. The difference between these two is +4. Between these two is 8, these two is 6, and so forth. Then, since these are not the same, we took the difference between those numbers. Okay, -6 and 4 is 10, and so on. Now, since these still weren't the same, we have to do it again. So the difference between these two is -6. Between these two is -6, -6, -6. So since it took us to the third difference, okay, since the third differences are constant, all right, since the third differences are constant, the degree of the polynomial function represented by this table is 3. All right, so this is a third degree polynomial because the third difference is the same. It's all constant. It's the same. All right, so this was the first difference. They're all different, so we have to do it again. This is the second difference. They're still all different. Had to do it again. This is the third difference. They're all the same. So therefore, since we had to go to the third difference to get them all the same, the degree of the polynomial function is 3. All right, the degree of the polynomial function is 3. If this red row right here had have all been the same, say these were all -8s, and then this column wouldn't have existed. If these had have all been the same, it would have been a second degree polynomial. If these had have all been the same, meaning these two columns wouldn't have existed. If these two were the same, it would have been a first degree polynomial. Okay? So you take the difference between the y values. If those aren't the same, you take the difference again. If those aren't the same, you take the difference again. Basically, you take the difference until all the differences between the numbers is the same. Once they're all the same, however many times you had to take the difference, that is your degree of your polynomial function. All right? So I know this video has gotten kind of long. So I'm going to go ahead and end it right here. That's your polynomials functions video. Feel free to watch it as many times as you need to. Make sure you come to class tomorrow ready to work some problems. See you tomorrow.